All right, let's just jump right in. We're going to take a trip today. A journey, really. Starting with these huge, glowing pieces of hardware that kicked everything off, and drilling all the way down to the tiny, invisible instructions that make our phones and laptops actually do something.
I mean, have you ever really stopped to think about it? You click a mouse, you tap your screen, and boom, a whole universe of stuff just happens in a fraction of a second. So today, we're going to peel back those layers. We're going to see how the magic trick is done, from the actual metal and silicon all the way to the abstract ideas that control it.
But look, before we can get to the ghost in the machine, the software, we've got to understand the machine itself, right? And to do that, we have to hop in the time machine and go way back to the very beginning.
So, when you look at this timeline, a really clear story pops out, doesn't it? Each big jump, each generation, it all comes down to one single revolutionary piece of hardware. We started with big glowing glass tubes, then we got transistors, then we squished thousands of those onto a tiny chip, and finally, we put the entire computer brain on a single chip. And you got to understand, each step wasn't just a small upgrade. Oh no, it was a total revolution. It's what made computers ridiculously more powerful while also getting smaller and smaller, paving the road that leads right to the AI we're all talking about today. So here it is, the granddaddy of them all, the vacuum tube. I mean, look at this thing. The first computers? They were literally the size of a room, just packed with thousands of these. And they were kind of terrible. Slow, super unreliable. They kicked out so much heat you could probably cook on them, and they basically needed their own private power plant just to run. And then, this little guy showed up, the transistor. It basically does the exact same job as that huge vacuum tube. It's just an on-off switch, but look at it. It's tiny, it's way faster, and it's so much more reliable. This, right here, this was the breakthrough that let computers finally escape the giant labs and start making their way toward our desks.
So what's the next logical step, right? If you can make one tiny transistor, why not make a bunch? In fact, why not figure out a way to print thousands of them, all onto one single tiny piece of silicon? And that's exactly what happened. This is the integrated circuit, or IC, and it was a total game changer. Computers got even smaller, way cheaper, and so much faster. This is when we started getting things called mini-computers, which, believe me, were still pretty big back then.
Okay, so the next leap, it just took that same idea and cranked it up to 11, the microprocessor. This is where they put the entire brain of the computer, the whole central processing unit, the CPU, onto a single chip. Just think about that for a second. This one invention, this is the heart that's beating inside every single PC, every laptop, every smartphone you've ever used. All right, so that's the story of how the hardware got so small and so ridiculously powerful. But how does it all actually work together? You've got all these parts. How do they talk to each other? Well, it turns out that pretty much every computer out there, from the phone in your pocket to a giant supercomputer, they all follow the exact same basic design. And this is it. This is the blueprint. It's called the von Neumann architecture. And it's actually really simple when you break it down. You've got the CPU. That's the brain. It does all the thinking. You've got memory. That's like the computer's short-term scratch pad where it holds data and instructions. And then you have input and output. Your keyboard, your mouse, your monitor. The stuff that lets you talk to the computer and lets it talk back to you. Brain, scratch pad, and a way to communicate. Super simple, but unbelievably powerful. So that brain, the CPU, what is it actually doing billions of times a second? It's just doing a simple little four-step dance, over and over and over. First, it fetches an instruction from memory. Then it decodes it to figure out what it's supposed to do. Then it executes the command. It actually does the thing. And finally, it stores the result back in memory. Fetch, decode, execute, store. That rhythm, that's the literal heartbeat of your computer. And right here, this is where that abstract idea becomes a real physical thing. This is a motherboard. Think of it as the central nervous system that connects everything. See that square socket? That's where the brain, the CPU, plugs in. And those long slots, that's where the memory, the scratch pad, clicks right into place. This is our von Neumann architecture, but made of plastic and copper. Okay, so we've seen this stage, right? We've got the motherboard and the CPU. But what about the actors? How does the software, that ghost in the machine, actually get on stage and do things? How does it find the props, the data? Well, it all comes down to the language of memory. I want you to picture something. Think of your computer's memory as a giant sports stadium. I mean, a massive one with billions and billions of seats.
Now, every single seat in that stadium has a unique number on it, right? Section 101, row B, seat 5, that's its address. And that's exactly how memory works. A program doesn't just vaguely look for that piece of data I need. No, it says, I need the byte of data that's sitting at address 6487624. It's that precise. It has to be.
Okay, so if every little piece of data has its own unique address, out of billions, how in the world do you keep track of it all? Well, think about it like this. You could write down a whole long message on a sticky note. Or you could just write down where to find the message, like the note on the fridge. That's a pointer. It's a special little variable that doesn't hold the actual data. Nope, it just holds the address, the seat number, of where the real data is.
Let's actually see how this works, because it's pretty cool. First, we make a normal variable. We'll call it A, and we put the number 10 in it. Simple enough. Then, we create a pointer. We'll call it PTR, and we tell it, your job is to remember the address of A. Okay, now for the magic. Look at this line of code. It says star PTR equals 25. The star tells the computer, don't change the pointer. Follow the address the pointer is holding, go to that location in memory and change the value you find there to 25. And what happens? The original variable A is now 25. We reached out and changed it from a distance. And this is so powerful. It lets programs be super efficient with memory, moving these little addresses around instead of giant chunks of data.
Now here's the thing. Pointers can be your absolute best friend in programming, or they can be your worst nightmare. You've got different kinds. A null pointer is the safe one. It's basically a pointer that's proudly announcing, I point to absolutely nothing, which is a good thing. A void pointer is like a skeleton key. It's a generic pointer that can hold the address to any kind of data. Super flexible. But then you get to the scary ones. A dangling pointer points to a memory address that's already been cleared out. It's like having a key to a house that's been demolished. And a wild pointer? That's one that was never given a direction, so it's just pointing to some random spot in memory. These last two, they are the cause of so many bugs, crashes, and headaches for programmers. It just shows you how careful you have to be.
Okay, so we know how software can find stuff and change stuff in memory. That's cool, but the real magic, the thing that makes software feel smart, is its ability to make decisions. How does a game know if you've won? How does an app know which screen to show you? It all boils down to some really simple logic.
The most basic building block is the if statement. You can think of it like a bouncer at a club. It checks a condition, are you over 21? And if the answer is yes, it lets you in to run the code. If not, you just keep walking. Simple. Then you have if-else. This is a literal fork in the road. If the condition is true, you go down the left path. Else, meaning otherwise, you're forced to go down the right path. One of the two has to happen. But what happens when there are more than two choices, like figuring out a letter grade for a test score? That's where you use the if-else-if ladder. The computer starts at the top and asks the first question. Is the score over 90? If the answer is no, it goes down to the next rung. Okay, is it over 75? If the answer is yes, it does its thing, assigns a B, and here's the crucial part. It jumps off the ladder. It completely ignores all the other checks below it. It's a super efficient way to find the first right answer and move on.
All right, we have covered so much ground. We've seen hardware evolve over almost a century, and we've peeked at the basic building blocks of software. So now, let's bring it all together. Let's make that final critical connection between the physical machine and the invisible code.
I mean, it really all comes down to this. Just look. On one side, you have a single, big, fragile glass tube that acts as a switch. On the other, a tiny chip of silicon that contains billions of microscopic switches. That journey, from 1 to billions, from the size of a light bulb to something smaller than your fingernail, that mind-blowing leap is the reason we have the world we have today.
And here's the beautiful part. All of that incredible hardware, the billions of transistors, the motherboard, the memory, it's just a powerful but dumb machine. It's just sitting there, waiting for orders. And what gives it orders? It's the simple, elegant logic of something like an if-else statement. That's the real ghost in the machine. It's just a simple choice, a fork in the road, that tells all that powerful hardware what to do next, turning raw electricity into something that feels like intelligence.
So we've gone from the physical world of atoms to the abstract world of bits. From room-sized machines to invisible rules. It's this beautiful dance between hardware and software that pushes everything forward. But it leaves you with a big question, doesn't it? As our machines get more and more powerful and our logic gets more complex, at what point does it stop being just logic and start becoming actual thought?